Okay, so welcome back. You guys have all now officially been through the hardest part of this class. Okay, if you can wrap your mind around what we just did, I mean, we just friggin' did a second order differential equation. We solved a solution where VR wasn't constant. It didn't even, didn't have the end behavior and the beginning behavior were the same. We just solved a very hard problem. This is not something that you come off of this like, well, it gets way harder from here. Quite frankly, this is about as hard as it gets in this class. And all of you survived. Although you're giving me that look like you may have died on the inside. Okay? I'm now... Tell Kate, if you slump any further, you'll actually be laying on the floor. You're almost there. Please don't hurt yourself. Oh, that's great. That's great. Let's talk about how to make that easier, okay? Now, in this class, and if any of you go on to take the FE, you're not going to deal with a system, not a constant DC voltage system, that looks any different from this. You may deal with a system where you have a constant voltage source, and here's a resistor, and then you have a capacitor, and you have an inductor in parallel, okay? The solution method is very, very similar. Here you have two loops. You have to do those calculations, but really it doesn't vary a whole lot. Because these problems are so complicated, quite frankly, oftentimes people just throw them to computers. At the beginning of class, we talked about node voltage analysis. We talked about mesh current analysis. That was many, many weeks ago. Those are the solution methods that would be used to solve more complicated problems than this. And there are programs that do that. So, for anybody trying to do this by hand, it's just not going to happen for anything more complex than this. But you should be able to, for those of you who are certainly mechanical engineers, for those of you who are going to electrical engineering, you have to know how to do this in order to pass the FE exam. So I teach this to all of you on purpose. Now for everybody else, this has to do with control systems, which is a class that all of you should be in next semester. Control systems is very heavy on, you will see that exact equation I wrote up there, you will see it again. It will come back and it will haunt you again next semester. Next semester it's not nearly as bad because we've already gone through this hard part. Okay? But it's still rough. This is hard stuff. This isn't child's play anymore. This isn't freshman level material. This is where you're at. And even then, this is a 300 level class. This is technically junior level material. And yeah, I know you're a junior. You're a junior too, aren't you? Yeah. They're both sophomores. They just have junior standing. It doesn't matter. This is junior level stuff. You're a junior, that's right. But you're like a you've been here for 3 years kind of a junior.
I'm an actual junior.
Yeah. Yep.
They held me back.
Well, I'm glad nobody's holding you back anymore. Motivational quote. Trace. Huh? You can probably wait till your senior year. But I think there was a conflict of classes. I don't know. I'll look at it after class. Thank you for pointing that out. Yes, there was a conflict because it actually, with thermodynamics and 350 are right next to each other, and EVS 201 was also at that same time. So I just went like, nope. I know, right? We've switched to philosophy. Did I spell your name right?
Yeah. No, you forgot an I before That's correct on his name. 45 minutes.
Tracy. It's awful. Okay, so one of the ways that we can make this simpler is by playing around with some numbers, okay? What we got for our S1 value is negative R over 2L. Well, it turns out, somebody read me the constitutive equation from our last problem.
Vs equals LC d squared VC over dt plus CR dVC over dt plus VC.
Thank you. Okay, so it turns out we can arrange this equation a little bit to get it to look a little differently. Okay, we're going to put this equation in the following form. Our forcing function, which is function of time, is equal to d squared over dt squared Vc plus 2 alpha d over dt Vc plus omega naught squared times Vc, okay? We're going to take this equation and change it into this one. And then I'll tell you why. First, we need to figure out what is alpha and omega naught squared? What? 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 Oh. Sorry, that was an inside joke. I used to work at a daycare. A kid who's, what? 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 Yep, that's on YouTube. So the first thing I'm going to do is, here, we got a 1 in the coefficient right here. So you know what? I'm going to divide everything by LC. Just get rid of it. And you know what? That fixes everything. So, Vs over LC is equal to d over dt, that's a squared, times Vc plus this divided by LC is equal to R over L, d dt Vc plus 1 over LC Vc. Okay? Ta-da! We got it in the exact same form. Now what this is if we compare these two, our forcing function, f of t, is equal to Vs over LC. That's 1. Alpha is equal to, well, 2 alpha equals R over L. That means alpha is equal to R over 2L. Okay, and omega naught squared is equal to 1 over LC. So that means that omega naught is equal to 1 over the square root of LC. Why did I do that? Well, it's for one simple reason. You remember how we had this really gross equation for S1 and S2? If we write the equation with these terms right here, alpha equals R over 2L, which you'll notice is right here. S is equal to negative alpha plus or minus. Now R over 2L times the square root of 1 minus 4 LC? What? What? Huh. That's fun. Turns out we can rewrite this as, this is the square root of alpha squared minus omega naught squared. If I did my math right. I might not have. It's supposed to be. You know what? There we go. This happens. So the beauty of writing this equation in this way is that it gives us a very simple S, a much simpler S. And this gives us implications. Now in the last problem I asked you, what happens when you want your S values to be equal? If S1 equals S2, then what that means is that alpha squared is equal to omega naught squared, which means alpha is equal to omega. If these two terms are equal to each other, this system experiences what's called a singularity, which is where the behavior is a little unique. Okay? If S1 equals S2, there is a very specific solution that we have to estimate. Okay? So, by the way, yes, something I forgot to tell you. Because alpha and omega, because they're under a square root, we're going to define a special variable now. So we've just defined two brand new variables, alpha and omega naught. I'm now going to define a third variable that compares them. And this is zeta. It's probably the least fun Greek letter to draw. Zeta is your damping ratio, and zeta is equal to alpha divided by omega naught. This is the ratio of alpha to omega naught. If zeta is equal to 1, it means that alpha is equal to omega. If zeta is equal to 1, this blows up because it equals the square root of 0, and then S is equal to the negative alpha, and then your end solution, your estimate solution for VCC is going to actually have to be A1e to the st plus A2s e to the st. Just because we have to have two solutions. And if S1 equals S2, we don't have two solutions. So we have to do this. Okay? So this is if alpha equals omega naught. Or I'm just going to write it as terms of zeta. If zeta equals 1, this is true. Okay? But guess what? That also means that your S is equal to alpha, negative alpha. So it's a little bit more complex, but it's also a little bit more simple. Okay? Now, on the flip side, Ben, at one point you had mentioned what happens when R equals 0. Well, if we plug R equals 0, I just erased the definition of alpha. Alpha equals R over 2L. Omega naught is equal to 1 over the square root of LC. If R equals 0, alpha equals 0. If alpha is equal to 0, we got problems. Because that means your S1 and S2t are equal to, well here, first of all, if alpha is equal to 0, your zeta value is going to also be equal to 0 because it's alpha over omega naught. Okay? If zeta is less than 1, what ends up happening is there is no way for energy to escape this system. Resistances allow for electrons to travel through a resistor and produce heat. The heat is a way for energy to leave the system. If there is no way for energy to leave the system, energy bounces between the inductor and the capacitor continuously. Okay? What you end up having here is it just goes tuk, 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 tuk. and it's a continuously oscillating system. It's really bad. But actually not for that circuit. For that circuit it would reach stability. Different story. But what we have for these is that not having a resistance still makes it a second order system. We didn't study RLC circuits. It just makes the system oscillate a lot. Okay? So for zeta less than 1, alpha squared minus omega naught squared is less than 1, which means you end up with S is equal to negative alpha plus or minus I square root of omega naught squared minus alpha squared. Okay? I brought the I out already because you know this is a negative value. Here, omega naught is larger than alpha, so I mean, this is just rewriting alpha minus omega naught squared, but just knowing that alpha is smaller. If you get this situation, there's a principle called Euler's law. When you take e to the I t, this actually produces a cosine function. That's Euler's law. Okay, e to the it or e to the I omega t is equal to cosine omega t plus I sine omega t. That's Euler's law. Your solution, if zeta is less than 1, is that this system now oscillates. This is called an undamped system, or an underdamped system. Okay? For zeta values that are greater than 1, your alpha squared minus omega naught squared is greater than 1. We don't have math problems. You end up with a solution that we had in our last problem. Okay? That's where your S is equal to negative alpha plus or minus square root alpha squared minus omega naught squared. And it is called an overdamped system. Okay? If we want to talk about how to make S the smallest, to make S the smallest, remember S has to do with your time constant. If you reduce the value of S here, what you end up doing is you change the value of tau to make it the most optimized value. Here, the most optimized value occurs right here. This system reaches steady state the fastest. It's called a critically damped system. Okay, here, this system reaches steady state faster than it should, and then experiences what's called an overshoot. So if I plot that out, if here's your steady state solution, okay? Let's say this is a graph of VC. And I know I'm out of time, so just let me draw this one graph. In an overdamped system, your solution looks like this, where it approaches the steady state solution as we know. That's what happens. Okay? This is overdamped. Critically damped has the same shape. It just does it faster. Okay? This is critically damped. And the last one is an underdamped system. Underdamped systems go much faster to steady state, but then experience an overshoot, where because this isn't flat, it then does this. And this is called an underdamped system. Okay? All right, I'll see you on Thursday.